Nakamoto consensus. So this is mostly going to be about the protocol underlying the Bitcoin blockchain, introduced by Satoshi Nakamoto. So to confuse things a little bit, I'm going to use similar terminology that Elaine used, but to mean different things. So let me start by recalling some of it. So when I say consensus, I'm going to mean the same task as what she meant with consensus. But when I say blockchain, I'm going to mean something else. And Elaine already hinted at that later on. So for now, consensus is what people in distributed systems have studied for a long time under the name state machine replication. So when I say consensus, that's what I mean. So what is this task? This is what Elaine introduced. So let me just do it again to make sure we're on the same page. So we had a fixed set of nodes. These guys would like to agree on an ever-growing log of transactions. Like in this example, this is Google. And they would like to have a list of transactions in Google Wallet. And they would like to replicate this whole database of transactions among these nodes. And the nodes need to agree on what these transactions are. This is what we refer to as consistency. And the second property is liveness, is that whenever some node sees some transaction that should be added to this database, to this ledger, then this transaction should be added sufficiently fast.
Actually, I have either 4 or 7 here, right?
Sorry?
You have 6 nodes.
I have 6 nodes. So there's no 2/3? Okay. What can you do? And so you want these two properties hold under some conditions, such as 2/3 or all but one being faulty. And we'll see various different assumptions under which this can be achieved. And Elaine discussed several of them before. So as you heard, this kind of creature today has many different names. When people say permissioned blockchain, this is actually what they mean also. And that's maybe more the more hip name of state machine replication. But really, this has been around for forever, or at least since the
why permission?
80s.
What's permission about it?
What's permission is that we have 7 nodes. You need to have permission to enter. Everybody knows who's allowed to be there. That's what a permissioned blockchain is. Okay? But really, permission blockchain is the same thing as state machine replication as defined by Fred Schneider in the 80s or something. Okay. Or a public ledger, same thing. Okay. But I will use mostly the name state machine replication or consensus. So let's recall these two properties of consistency and liveness again. So consistency says the following: take any 2 nodes at any given point in this execution. So me and Mohammed, we look at the logs that we have, and we should agree. At any given point, we should agree. What does it mean to agree? Well, potentially, he has seen a transaction I haven't seen. So either, and that's fine, right? Because some transaction came to him first. It hasn't propagated over the network yet. But what we mean by agreement is that either my list is a prefix of his, or vice versa. Okay. And it turns out that actually just consistency between any 2 players is not enough. You need to be a little bit careful in how you define this. And you also need this other thing, which today is called future self-consistency, that I need to be consistent not only with everybody else at any given point, but also with my future self. Okay. So consistency says, taking it 2 guys, we agree at any given point. And also, what I have today agrees with what I will have in the future. Okay. And liveness, this you heard about this morning, and it was discussed quite a bit. So it just says that there exists some fixed polynomial t that says how long it takes for a transaction to be confirmed. Okay. So whenever some node receives a transaction as input and would like to get it added, that transaction should be added to everybody's ledger within t steps. And this t could actually be parameterized by the maximal network delay. So we have some parameter delta that determines the maximal delay it takes for a message to get propagated on the network. And of course, if it takes a long time, I cannot hope it to arrive at everybody fast. So it needs to be a function of this network delay. And as you also heard this morning, there are 2 main models in which these type of consensus protocols have been studied. The first one is the cleanest and simplest synchronous model. So in this model, we have this maximum network delay, and the protocol can be parameterized to it. Okay? So the easiest way to think about it is that the protocol proceeds in rounds, and every round you wait 2 delta steps, let's say, to make sure that you received all the messages for sure, and then you move on to the next round, and you send your message, you wait 2 delta or something like that. Okay? So that's the synchronous model. These protocols are loved and also hated because they take a long time because you have to wait for this maximum network delay, which is annoying. So there are these nicer type of protocols called partial synchronous protocols, where the same protocol should work for any delta. So the protocol is unaware of what delta is. Okay? So my protocol is not parameterized by this thing. It kind of usually proceeds very, very fast. And typically when delta is small, it will go fast. When delta is long, it will go slow. Okay? Because it's unaware of what delta is.
You're using partial synchrony in a different sense than Elaine used.
So yes, that's what I'm saying. I use slightly different. So the original paper on defining partial synchrony by Dwork, Lynch, and Stockmeyer, this was the main way they defined it. Then they defined a slightly different way, which was a GST, the way Elaine used it. Typically, these models are the same because of some doubling trick. But this is kind of the simpler way of explaining the model. Okay. Okay, so just to make sure we understand what these 2 properties imply and why we like them so much, the point is if you have a protocol for running this type of consensus that satisfies consistency of liveness, that means in essence, this protocol implements a trusted public ledger. So think of it as having a trusted third party to which you give transactions. Whenever somebody wants, they can send him a transaction. He makes sure to add it within t of delta time. Okay? And then anybody can come and look at, can ask the trusted third party, and the trusted third party will give you a prefix of what he has stored up to something close to delta time. Does it make sense? So really, this is very nice because you can really think of it as having some stone where people are writing transactions into it, and people can observe this stone. We might not see exactly the same thing, but we're very close. Right? Maybe there's some gap in what we see, but it's only going to be based on something small based on delta. Okay, so quickly recalling how this classic traditional model proceeds and some key features of it. And that's why it's actually today called the permission setting. So what makes it permissioned? Well, the key thing is that the number of players, n, in Elaine's talk, is fixed. And everybody knows it. Just like we do in normal crypto. We receive the number of players. That's an input to our protocol. Right? We know it. Not only we know how many people are there, we also know their names. I need to know who I'm talking to. It's all of us talking. We know who we are. Okay, this is common knowledge. Additionally, classically, we focus on a setting where nodes stick around. If you want to be part of this protocol, you're there from day 1, and you're there until the evening when it's time to go home and sleep. Okay? There's no breaks. You come, you work, and then you go home. And the third thing, which is actually potentially the most important one, is we assume that we're communicating in a way that allows us to authenticate ourselves to one another. Okay? And there are 2 models typically considered. Either authenticated channels, which is just we have some channels to one another, the point-to-point model that Elaine mentioned, where when I send a message to Mohammed, he knows it comes from me. And another model, which is a stronger model, is this PKI model, where we assume that we additionally add some setup, have some somebody providing us with some public keys and secret keys, and the set of public keys is actually commonly known also. Okay, so there are 2 different models. And in fact, so these 2 different models, as you heard this morning, give rise to different type of results. Right? So in particular, summarizing the state of the art, or not, well, this is old stuff from the 80s, right? The main results here are we really understand exactly what's going on. Right? If you don't care about efficiency and run complexity, in terms of feasibility, things are very well understood. In the synchronous model, Remember, now the protocol is parameterized by delta. Then things are possible with authenticated channels if 2/3 are honest. And they're impossible, and you saw the impossibility results, if less than 2/3 are honest. Okay? So you can do something without a PKI if 2/3 are honest. And if you additionally have the PKI, then this beautiful Dolev-Stroll protocol works no matter how many people are corrupted. Okay, so there's a difference between authenticated channels and PKI. You can do better in the PKI model if you additionally have one-way functions. And that's that. But 2/3 without PKI is the best you can do. And in the partial synchronous setting, things are harder. In fact, 2/3, you can still do it. But here, a PKI doesn't help, and 2/3 is just the best you can hope for. Okay? So this is what you should remember from the classic setting. 2/3, it's possible, even with partial synchrony. No need for PKI. But in the synchronous model, if you have PKI, you can handle any number of corruptions. And in the partial synchronous, a PKI doesn't help. Eli?
What is the result that PKI doesn't help in the partial synchrony?
It's a very simple argument.
As far as I know, the result of the Dolev and Strong reduces.
Dolev-Strong is PKI.
What?
Dolev-Strong has a PKI.
So, but you say PKI doesn't help.
It doesn't in this, but Dolev-Strong is not in the partial synchronous model. Dolev-Strong assumes synchrony, very important.
Dolev and Strong,
Yes.
essentially, if you think of it, reduces Byzantine into fail stop. And fail stop, we can do partial synchrony.
Okay, let me give you the impossibility result. Okay. So you have how is it? So you have two guys.
No, take 3.
Well, I need 3, of course, but we have two guys here. These guys are talking very fast too.
Let's not get into breaking symmetry. Take 3. So.
There are 3 players, right? These two guys are talking very fast to one another. How is it? This?
Split range.
So this guy is going to either.
They can't talk to each other.
So the 2 fast guys are.
They're 2 slow guys.
These 2 guys are slow.
And then that guy needs to simulate 2 guys.
Let's not solve it now. I know that PKI reduces Byzantine.
No. There is a possibility. It's very simple. I'm just like blanking now on the.
So the left guy simulates 2 guys and talks to both of these guys who have long delay.
Yeah.
The left guy simulates 2 guys.
Left guy is.
Simulates 2 guys.
Simulates what?
2 guys. There's P1, P2, and P2. Yeah, he is a single guy, but he's acting as 2 guys.
Yeah.
And one talks to Q1 and the other talks to Q2.
This is Q.
Yeah, this is Q1 and the other is Q2.
Where is Q2?
Q2 is
the one below.
long delay.
Yeah.
Yeah, and Q1 and Q2 have long delay.
Mm-hmm.
The messages take forever. And then P1 is playing with Q1 and P2 is playing with Q2. P2 is playing with Q2, running the honest protocol.
Yeah. So these guys are running on input 1.
Yeah, P1 is running with input 1 and P2 is running with input 0. Let's say P1 and P2 are the senders. We shouldn't do with broadcast. We should do a binary agreement.
Okay, let's take this offline. The point is, there is a simple possibility. We're kind of now, I'm blanking on it, but I can explain it after.
I have one more question.
Yeah.
In the synchronous network model, like I thought always that the rule of thumb is that you can make synchronous up to 1/2.
So in this model, where you're dealing with consensus, this is the same question as was asked this morning. Right now, all the nodes are being present there. Okay. In that case, in the synchronous model, you can do Dolev-Strong and do rotating guys, and you can handle M-1 corruption.
So one way to say it's not publicly verifiable.
It's not. This is like, look, in this thing we have this. Only these guys are participating, and I only want consensus among these guys. There are no outside people. Only these guys need to agree. This is what you want when you want to have a database in a distributed way. Only the nodes that are participating should agree. I don't care about any outsiders.
Okay.
What's the definition? The dollar-strong properties for broadcast.
$strong is a broadcast, but you can easily turn it into something that works like this by just rotating leaders. First, the first guy goes, he sends something $strong, then the second guy goes, and so on and so forth.
I could say it slowly.
So first I go, then Mohammed goes, then Itai goes, and everybody sends their the transaction with broadcast using $strong. So that's a way to get an ordered list of transactions.
Okay. Because we know the consensus, the classical consensus, not Nakamoto, not state machine replication.
No, yeah, that's different, yeah. So now I'm talking about state machine replication. Among these nodes, this is the definition. It can be done n-1.
What's the definition of PKI model?
PKI model is that you have, for simplicity, for now, let's assume that we have some honestly generated public keys and secret keys. Okay. There are many different, usually these results like $strong actually work in a weak, what cryptographers call the bare public key model. But for now, simplicity.
Because of the plus one-way function. Why isn't one-way function implied by the PKI model?
There's no, I'm just saying you need digital signatures. I want the digital signatures. Yes, the implication is not. In the PKI model, you need digital signatures. You can actually sometimes get away with information theoretic things also. If you want it for a bounded number of times, you can have these transferable things. They're just more annoying. But I was just trying to simplify things here. OK, so what I'm going to talk about today is this different setting, which is what Nakamoto is in. OK, and that's this permissionless setting. So the permissionless setting was kind of introduced in Nakamoto's paper from 2009. And the idea was to be able to run these type of consensus protocols among anybody who wants to join. Okay, that's why it's permissionless. There's no need to have a permission to join. You don't have to be one of the servers at Google. Anybody can be part of this thing. Okay. And in the first block, he had this text about the chancellor on the brink of second bailout for banks. He was clearly motivated by the fact that there might be this financial crisis, and the banks are not to be trusted, and they could screw the users of the money, right? So they wanted to have a system where the banks are not in control of our money. So what I'll try to do today is try to discuss some of the key features of this permissionless model and how it differs from the permission model. And really, all of the three properties that I stated before are now gone. And we'd like to handle this kind of a lot more adversarial scenario. So the first thing is, we don't know how many other nodes are out there. But anybody should be able to join, so I don't know how many people are there. Okay, remember, before, we knew exactly how many there were and who they are. Second of all, this thing that nodes can come and go. This is also referred to as late joining. This one perhaps is not so new. That has been around actually before, but it's became more relevant now. And then the third thing, which as I mentioned was perhaps the most pertinent feature, is there's no authentication mechanism. Right? There's no pre-established PKI. And we don't assume that the existence of authenticated channels. We're just talking to people. I don't know who they are. Okay. Then finally, here's a kind of today not a mathematical property, but it's some kind of like desiderata that we'd like to get these protocols, since they're running among everybody in the world, we'd like to get some kind of economic or game theoretic robustness. Okay, this is kind of vague, and I would like to focus on more the kind of distributed computing problem, so as a normal computer science problem. So I'm going to today skip this thing for now and get back to it later on, because this is kind of not exactly clear how to define. So I'm going to just focus on these things, and these are very well-defined mathematical ways of modifying the classic model. And so as you see, this is a much more challenging setting. Right? We're letting go of assumptions. We're shedding them one by one. And so now the question is, what can we do? Right? And we really are, I would argue, still in just the beginning of understanding this model. It's quite different. So let's start off by just focusing on this thing, which, as I mentioned, was perhaps the most pertinent feature, that we don't have any authentication mechanisms. And let's see what happens when you remove authentication from the classic setting. In fact, this thing was a model that we considered together with Ran Canetti, I don't know if he's here now, with Boaz Barak, Canetti, Lindell, and Rabin in 2005. So we said we'd like to design cryptographic protocols in a setting where we don't have authenticated channels. Okay, and what can be done? And the first kind of observation already in the intro is actually you can't do anything. Okay? So we were looking at a scenario which was in a partially synchronous model. And there is actually a trivial impossibility of consensus without authenticated channels in a partially synchronous network. So let me just very quickly show it if I remember it. So we have, let's say we have some set of nodes here. There's lots of nodes here that would like to agree on something. And here is a final guy that actually should have been there talking to them. But what I'll do is I'll pull him out. And I'll actually not let him talk to all the others. And then I'm going to here emulate all the others for him. So right now, this guy, the way he sees the world is he's talking to this simulation that I'm performing for him. Okay, this is kind of the nightmare you might have, that you wake up and you're just living in a simulation. All these people are so nice to you. They're actually not the real ones. You've been actually abducted by an alien, and they're just doing it to do some kind of like rewinding to extract that stuff from your brain. Right? So this is what happens to this guy. He's here now. He's talking to this simulation. And so these guys are now running the protocol with, let's say they're putting in some transaction A, B, and C. And since this protocol is secure, they should output these protocols, these transactions A, B, and C. Right? Now this guy, what does he see? Well, he's talking to these guys, and maybe here I'm running it with some X, Y, and Z. So now he should be outputting X, Y, and Z instead. Right? So now we have broken consistency. So by liveness, these guys will output A, B, and C. And this guy by liveness will output X, Y, and Z. And therefore, we've broken consistency because they output different things.
To clarify, the reason why this is possible is because there are not integrated channels or PKI. So this simulation is actually something that can be done.
Exactly. So I'm just separating this thing, and it can be done. Note here that one very important part of it is that this guy doesn't see these messages coming from these guys. Right? And that is possible because I can actually, these messages, they want to send things to him also. Okay, they might be flooding it on network, say, please send this to Alessandro. But I can actually, all these messages that they want to send to this thing that maybe are flooded on network, I'm going to delay them. And I can delay them for very long. And if I have a protocol that's partially synchronous, these guys need to provide an output even after this has been delayed.
How do then the authenticated channels help here with these delays when they're So you said without authentication this attack is possible, but then like that means
with authenticated channels I cannot simulate these messages, right?
Okay.
So this is like, so right now what I'm doing this, I need to be able to do this kind of costless simulation where I can simulate everybody else in the world. Yeah. With authentication.
You can still separate the node out of the network, right? And then
I can separate the node out of the network, yeah, and he doesn't, but that's okay because he doesn't need to provide an output until the message comes. Okay?
You need a different example for the synchronous case, right?
Yes. So right now, this was like the early one from what we had. This was like a simple observation, but we took it as saying like this model is kind of it's an interesting model to not consider authentication, but we said that we can never hope to get consistency. So what we did in that paper was instead considering a model where you could do secure computation without consistency. Okay, so we said like, look, I can never hope to prevent this thing, but we can consider some model where at least this execution should be independent of one another. And that turns out to be actually, even that is non-trivial to do. But so we give up on consistency and dealt with a notion security where you can define other security properties, but just giving up on consistency. Okay. All right, so the synchronous thing turns out to be a little bit trickier. Okay. And so the problem here is that this guy might now hear these messages also. So now he's getting confused, right? He will hear what I'm doing X, Y, and Z, but he will also hear these A, B, and C messages. So he will output X, Y, and Z. He will also output A, B, and C. Okay, potentially, right? I'm not sure what this protocol does, but there's nothing that prevents him from also outputting A, B, and C. Right? I'm getting this conflicting thing, but maybe the protocol tell him that, like, you know what? I hear too many things. Let me just play on both and output everything. So this doesn't quite work. And likewise, he could start sending these messages to these other guys, and they will also output X, Y, Z. Yeah. Okay, but there is actually a way to modify it, and this is based on this old impossibility results from the classic distributed consensus literature, in particular this impossibility result by Fisher, Lynch, Merritt. Was it the right one? FML. So let's see if I remember it. So let's say we have 100 people out there. And let's split them into two groups. So here we have 50 of them, 50. We'll call these guys P. And this guy's Q. Let me actually call this guy P star and Q star. Okay? So I'm just bundling them together. Okay? And there's a bunch of messages being sent between them, and there's a bunch of messages being sent between P and Q. So let me just write this message like that. Okay. And these guys, I'm going to start running them on some. I'm going to sample some transaction that has a random number. Let's say. Let's call it TX. T0. So this is a random number and bit long string. Okay. Okay. And now, so these are the two honest guys. They should be running with one another, and if we run this protocol honestly, they should output this transaction, right? Great. Now I'm going to also create some noise for them. How will I do that? Well, I'm going to simulate here to him some Q. And here I'm going to run it on some dummy input. Okay? And then some other noise here. Some P on some dummy. And I'm going to do this very long circle. Very, very, very long until I get to some other P here and Q there. Okay, let me call them tilde. Okay. And all these guys are running on dummy. And then this guy, I'm going to run on some other transaction T1 that's also randomly selected. Okay, does it make sense? So these two honest guys are running as usual. But right now, I'm also pretending to be the Q guys to him. So now he hears double noise, right? He hears the real thing, and he hears other messages that are pretended to come from them. He doesn't really know which one is the right one, but as we said before, he might be able to maybe output both. Okay? So let me argue that we'll have to get to some contradiction here. So we said that these two guys are going to output T0, right? Additionally, what I would argue is that any two consecutive guys, they're going to output either T0 first or T1 first. So they need to have a log of transactions, right? Everybody has a log of transactions that they're outputting. So either T0 is above or T1 is above, right? By symmetry, let's assume that T0 is above T1. Okay, or maybe T1 doesn't appear at all. So let's assume here that T0 is output. Okay? These two guys, by consistency, need to output the same one first, right? Therefore, these two guys, by consistency, also need to output T0 first, right? Because these two guys are just like two honest guys.
Who's these two guys? Who's the Q to the left of P prime?
These are just people acting exactly as the nodes in Q.
Huh?
People acting exactly as the nodes in Q.
Yeah, but in the
There are Q nodes.
Everybody talks to everybody. Suddenly you make this long ring that people don't talk to each other, and I thought that this is the problem.
No. Here I'm saying that I am doing the links, right? This guy's talking to this guy's talking to that, right? This is just in my head. The way these two guys view it, they have only access to, they get messages from him, and they get messages from this guy. This is all reality, right? The way around the attack is like these two guys are the honest two guys, and then there's some noise I'm giving them. Okay? So what I'm arguing is like, in my emulation, in my head, these two guys need to also output the same thing. This one needs to come first. So T0 needs to come first here too. Okay? So T0 comes first before T1. And so on and so forth. And by consistency, everybody needs to output T0 first. Okay? Now, how fast should I output T0? Well, something that depends on delta. Okay? It was this big T of delta. Let's say it's within 1,000 steps. Okay? Now, if this ring that I'm just doing in my head is very, very big, much bigger than 1,000, then there is no way that this T0 could have propagated down to here. Right? Because he gets some message from here. After the first step, maybe this guy learns what T0 is. But he will only, in that case, be able to tell this guy after 2 steps, and so on and so forth. So you can now just say that, in this after T steps, only people up till they're T steps away from this guy could have ever heard about T0, information theoretically. And therefore, there's no way that this guy could have output T0. And that's it. Okay? So, the point is, without authentication, we're doomed. And this is where Nakamoto comes in, because he says that we're not doomed without authentication. We can do it anyways. Right? So, so how does he do it? The whole point here was that when we did all these arguments, it required us to be able to simulate lots of other players in our head. Okay? And Nakamoto would like us to be able to prevent these type of simulation arguments in our head. And how can we do it? By requiring people to work hard to participate in the protocol. Okay? And that makes it impossible to do this type of Sybil attacks where I'm simulating lots of players, because simulating lots of players requires a lot of computational resources. Now, that alone is not good enough. To just using proof of work doesn't overcome these lower bounds, right? We also need to change the model somehow. And the way he changes the model is to say, I'm not going to say that a certain fraction of the players are honest, because fractions of players doesn't mean anything in this setting, because we can do this, I can simulate anybody I want. So instead, I'm going to make the assumption that a majority of the computing power in the world is held by honest players. Okay? So I'm going to have a protocol that's computationally intensive to run, and then make the assumption that the majority of the computing power is honest. And then under these two things, he claimed that he got something that actually satisfies this kind of state machine replication, satisfying consistency and liveness. So that's very nice. So let me point out there are two really amazing aspects of this thing. They're really worthwhile. Well, the first one is that it overcomes this unauthentication problem. That's really what he wanted to do. But note something else. He claimed that it was secure under just an honest majority. Okay? There was no PKI in the setting. This also overcomes this 1/3 barrier that we saw from Elaine's talk, somehow. And it's actually very insightful to look at exactly how that previous impossibility breaks down. Right? Because that was a very convincing possibility. Right? What happens here in this authenticator setting? Well, note here that in this argument that Elaine did, the attacker, right, even when I have authenticated channels, needed to simulate these 3 other players, not just himself, but actually needs to do 4 people in its head. So right now, if all of them were spending computational resources, he's actually spending a lot of computational resources. Right? He's actually spending 4 times more than an honest guy. So the number, the amount of computational resources he's spending is way more than honest people, so it doesn't overcome Nakamoto's. Right? It's no longer honest majority in terms of computational resources. Okay. So the point here is that by switching this perspective to counting computational resources, and by having protocols that are computationally expensive, we can actually potentially overcome these barriers with dealing with without authentication, and also getting above this 1/3 barrier and getting to 1/2. So for the rest of these 2 hours, out of which there's not much less time left than I would have hoped for, what I will try to go over is first kind of an abstract notion of a blockchain. Okay. So I'll explain what the blockchain protocol is, and then define some kind of abstraction that is a little bit more refined than just state machine replication. And it turns out that it's actually useful to have an abstract notion of a blockchain that's not just state machine replication. And I'll explain why. And then we'll discuss whether Nakamoto's protocol actually works. And originally, there was a little bit of confusion on whether it works or not. So in the original paper, Nakamoto, he showed that certain classes of a very natural type of attack that he analyzed doesn't work. But of course, that's just one attack. And there could have been many others. And there were many subsequent, or a few different subsequent works. Most notably, this very beautiful work by Garay et al. That really started off by having a very formal way of analyzing this protocol. That showed that large classes of attacks don't work. Then at the same time, there were these kind of attacks on it. And in particular, there was a claimed attack showing that by making use of the fact that there are network delays, in particular, assuming that there are 10-second network delays on a network, they claimed a 49.1% attack. So an attacker that only has 49.1% could break the protocol, they claimed. So maybe you don't reach exactly 50, but it's kind of okay. At this point, it's not clear what the answer is. Do we, will this attack be improved, or can we show that it's kind of tight? And so it turns out that right now we have good techniques for arguing that actually, as long as you set the parameters of the protocol correctly, it is secure. All right, but let's start by discussing what a blockchain is and how this blockchain protocol works.
Secure with what number?
With what number? We'll get to it later, okay? Turns out that number actually, they had a calculation mistake. So it should have been actually 49.8. We'll see what it is, 49.8, I think, or something. So we'll get to it. All right, so what is a blockchain? This is what a blockchain is. This is the abstract notion of blockchain. You have a bunch of blocks on a chain. Now you know. A little bit more concretely, let me start off with Nakamoto's original protocol. And most of you probably have seen this protocol. But let me do it anyway, slowly, just to make sure we're on the same page. So we'd like to chain together blocks of transactions. And let me show how to do it kind of inductively. So let's say that we have already generated some kind of chain of transactions. And how should we add some more transactions into this chain? So let's say that Eli would like to give Alessandro 50 bitcoins. Okay, and this is one of these transactions that's bundled together into a block. Just a funny story here. Like when I first gave this talk, this was roughly a bike. Okay, a nice bike, but still a bike. And today it's a nice house in Berkeley that I took from Zillow this morning. So not Ithaca. I looked on Zillow. This is from this morning. This house. You can look it up yourself.
So you didn't update the slides since then?
No, this I updated. You see. The slides on this part of it were.
Did you check if they accept bitcoins?
Yeah, I didn't.
Do you have that many bitcoins?
I don't actually. Yes, this is like instead of doing these slides, I should have bought instead of this bike that anyway got stolen later on. You know, it's. I would have had a house in Berkeley. Okay, so we have this set of transactions. We bundle them together into a block, and now the protocol, Nakamoto's protocol, is extremely simple. This is what it does. It asks everybody who wants to participate, and now anybody can be here and participate. They will take this new block. They look at the end of the chain up until this point. And they put the end of the chain, which is the hash of the current chain, the new set of transactions, and some random number, and they put it into hash function. That's it. That's what everybody does, and they start hashing. Okay? If the output of this hash function is some small number, then we say that they have found a solution to a puzzle, and we refer to this green thing, the random number, as the puzzle solution. And we're going to refer to D here as a difficulty. So the smaller D is, the harder it is to find a solution. And this is it. That's what everybody does. It's extremely, extremely simple. If you compare it to even the simplest protocol that Elaine was showing towards the end, you know, it's hard to, this is kind of dirt easy, right? All you do is take a new set of transactions, hash it, everybody just hash. If you find a solution, great, boom, you found a new block, and you send it to everybody. And the only thing everybody does is this. So I'm going to, for now, assume that this hash function is a random oracle, and that's going to be very useful for analysis. So what this means is that the best way you can find a solution to this puzzle is through brute force search. Okay. There's one extra subtlety I need to clarify in this protocol. And that is what happens when I join the network, and I see one chain like this, and I see a chain like this. Which one should I be trying to extend? Well, it's very straightforward. You do the natural thing. You go by the longest chain. Right? That's what it says here. So if I see two different chains, I'm going to always believe the longest chain, and I'm going to always try to extend from the longest chain. And now this is the whole protocol. So me, I want to join to participate in this protocol. What do? I go and ask all the nodes out there, what is the longest chain now? They tell me what the longest thing there is. Then I start mining. I start trying to confirm new transactions by putting in puzzle solutions, random numbers, and try to extend this chain. That's it, the whole protocol.
You also want some guarantee that the genesis has not been like pre-mined 50 years ago.
I need to have some guarantee that like this random oracle, yes, you don't. This is a random oracle, you cannot predict it. Yeah. But I need to assume it's a random oracle, right? That it's a fresh random oracle, yeah. Okay, so the question now is, does this satisfy consistency, right? That's what we want to ask. So now Eli, since he's an organizer who didn't show up, he deserves being publicly shamed. So let's say that you know he gave this, he was buying this house or bike from Alessandro, and he paid him this 50 bitcoins, and then he decides, I don't want to pay, right? It would be much better if I could get back my money. So what should he do at that, to reverse this transaction? Very easy. The only thing he needs to do is to find some other chain that's longer, that kind of like eclipses this thing, right? So if he goes back to here and says, let me rewind the past to the past and try to get some chain that's longer. Then I can erase this transaction and I have my money back. I can spend it. So to do this, he needs to find a longer chain. So how can he do it? Well, Nakamoto's claim was that if this transaction is actually sufficiently deep in this chain, then it should be safe. And in fact, what Nakamoto proposed was if there are 6 transactions after it, 6 blocks after it, then I'm fine. So really the way you should think about this blockchain is you look at the current chain, the last 6 blocks are not really fully confirmed yet, but everything before those 6 blocks are fine. Okay. And to get an intuition for why this is the case, note that if this transaction had been, let's say here, it's the last one, had just been mined, okay? Maybe let's get here. So we have this chain. Okay, so here Ellie gives to Alessandro something, and this is the last that has been mined. What should our attacker do to try to? What should Ellie try to do? Well, he will try to mine something else here, right? If he has, let's say, 45% of the resources, like 49 for simplicity now, then with 50% probability, he's going to find this thing faster than the good guys extend this, right? And then with another 50% chance, he's going to be able to find this thing. Right? So with roughly 25% chance, he's going to be ahead. And what happens when he's ahead? Then all the good guys are like, well, this is where we should be. Okay? So that's the intuition. That if it's like towards the end here, it's very easy to do this. But if you're further away, then you need to be lucky, sustain this luckiness for a very long time, and that's going to be very unlikely.
Why 6 is not...
No, it's not very, 2 to the minus 6 is not great. But, maybe it's good enough. So I don't know what the probability of fraud is with the Visa, but it's maybe on the same order.
maybe.
Sorry?
Yeah, maybe.
Yeah, I guess I'm not... I assume that like if the probability of fraud in Visa was much smaller, maybe they would have... it's up to you. You maybe don't want to wait 6 blocks, you wait 20, okay? Okay, so Nakamoto showed that...
Nothing magical about majority of computing power, right? And if you have a smaller fraction of computing...
It's much harder, yes, yeah. Then the probability goes down also, yes. So majority is... this is now... this is the most adversarial setting.
The paper would have been rejected
because 2 to the minus 6, yes. Maybe it was, who knows, right? Okay, so Nakamoto showed that just this approach doesn't quite work. As I mentioned, Garay et al. Had this very nice analysis showing actually that no attack works in a setting where you assume that delta is 1. So this is in this lockstep model where whenever I send a message, it gets to everybody in the next round. Okay. And then Sampolinsky and Zohar had a way to also deal with bigger deltas, but now they're back to a setting where they didn't deal with all attacks anymore, but only some certain classes of attacks. Okay, and as I mentioned, right now we know how to do it for all attacks. But before going to formalizing what we know about the security, it will actually be helpful of defining this more abstract notion of a blockchain. Because it kind of not only help the analysis, but this abstraction is useful if you want to use blockchains also to other things, not just to state machine replication. And in fact, there are several works that try to use these more advanced features also. Okay. So the first thing is really just trying to formalize this consistency notion that Nakamoto kind of envisioned, which is a little bit different than standard consistency. in state machine replication. Remember, the standard thing is that at any given point, my log is either a subset of yours or vice versa. There's no cutting off things. So here, we have this abstraction that what we want to say is that if I look at any two people's chains, what we view as their longest chain, if I get rid of the last k blocks, where k is a security parameter, then we should have consistency. Very natural, right? So take any two guys, get rid of the last k things, then accept with exponentially decaying probability in k, we should agree.
Probability over what?
Probability over the execution.
The coins actually.
The hash function is modeled as a random oracle, and I think it's over there.
There's the attacker, the players of randomness, and
But the good guys in the random work.
the good guys and the random oracle, yeah.
But the good guys, so you have, there are good guys and there are attackers. It's not that everybody can be an attacker.
So the way we model it is there are good guys and a single attacker that controls all the attackers. Right? So there's a single attacker, let's say, right? He's trying to break consistency. Okay. Point out that consistency again is subtle. You need this future cell consistency that we already discussed before. Let's not do it again. Yeah. All right, here's another property that, as far as I know, was first introduced in the paper by Gray et al. And it's a very useful property. And it talks about something called chain quality. So chain quality considers, when I look at this chain that everybody has, what fraction of these blocks have been mined by good players? So now when I define it this way, what fraction have been mined by good players, that's very tailored to the actual Nakamoto protocol, but you can actually give an abstract way of defining it. And intuitively, you would hope that if I'm controlling a p fraction of the computing power, I should contribute a p fraction of the blocks. Okay? So chain quality measures actually what fraction of the blocks here are contributed by good nodes. Okay? So I said in ideal scenario, if I have p fraction of good guys, you should get p. You might not get it. You might have worse chain quality than that. Okay?
It should be except with probability x minus k.
Yes, except with probability, yeah. Or with 1 minus epsilon, yeah. Okay, and the final thing is I would want this chain to grow not too fast and not too slow. It should go at a steady rate. It should roughly grow proportional with like 1 over network delay. Right, so with network delay, I'm never send a message, it gets there within delta, so roughly every delta step I should get a new block. Something like that, right? That would be ideal, to every delta step get a new block. Okay. So note that this chain growth property is actually quite interesting in its own right. It kind of says that it's a way to get a trusted clock. If I just look at the length of the chain, it's going to be ticking along, okay, at a steady pace. Okay? And so this is a property that's already more advanced than normal state machine replication. It's actually, this property is very useful when you want to build things on top of blockchain also. Later.
But why are you concerned about the high speed? Or what? I mean, I see that you want to grow at a reasonable rate, but
why you want to upper bound it?
Why are you concerned if you?
Because exactly this thing, I want it to actually behave like a clock.
Oh, because of that.
I want to, yes, it's several applications when you want to build new protocols on top of Nakamoto. It's very useful to know that the chain cannot just like suddenly run too fast either.
Steady variance? Because I mean, just because you have a fast clock, it's a fast clock. If you have a slow clock, it's a slow clock. I mean, so steady, I agree with. But I'm not getting why it has to.
Why can the steady be very fast?
Why it cannot be faster than 1 over delta, or what?
Well, why can the steady be really fast? You said you don't want to be too fast, you don't want to be too slow. It's clear why you don't want to be
No,
too
I want it to be something fixed, so I can use it as a clock, right?
But it's not about the fast.
No. But it turns out that you need to be, like, you cannot hope to do better than 1 over delta. But, okay, so just to make sure we understand what these three things do, let's just do a very simple proof that these three properties on their own imply state machine replication. Okay? So, how should I get a state machine replication from a blockchain? Well, the natural thing is run this blockchain protocol, and then cut off the last k blocks and output that as your log. Okay, so that's the construction of a state machine application from a blockchain. Why will it satisfy consistency? Well, trivially, by the definition of consistency from the blockchain, we said if I cut off the last thing, then we agree. So that's trivial. So consistency really is trivial. Now, why liveness? That's a little bit more subtle. Well, liveness follows from the following reason. By chain growth, I know that this chain is going to continue growing. Right? It'll never stop. Boom, 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 boom. By chain quality, I know that a certain fraction of these nodes are going to be by good guys. Now, good guys are going to include all the transactions that are here. So therefore, as long as I have a good block, it's going to include every transaction. So whenever I hit that, I know it's going to appear there. So therefore, we have liveness. Okay, does it make sense?
For liveness, you don't want just the chain growth to be steady. You want it to be steady and fast enough.
Yes, definitely. Yeah. It cannot be too slow. It needs to be growing at a certain reasonable pace. Yes.
Why is it to be fast enough? I mean, you can just include enough transactions in a given block.
Yeah. So for these two things, if you just want this, you don't need an upper bound on the chain growth. You just need a lower bound. You want it to be sufficiently fast. Okay. There are some other applications, I won't go into them, where it's actually very important to have this upper bound also, in order to get this clock feature.
And lower bound is just bounded away from zero, basically.
Yeah, it should be something that's proportional to 1 over network delay. In order to get that liveness property, I need it to be something with 1 over network delay.
Rafael? So, but this doesn't really yet cover the permissionless model, or at least the property of people being able to come and leave, right? Because I guess if the difficulty doesn't change and more people come, then blocks will not grow at the same rate. They will actually become faster. And
okay.
It's also not clear what's like the 50% of what, like the total ever network rate, or the total that it's on.
Yeah. So I'm trying to hide this thing about people coming, leaving too much. So right now, with the way I'm going to state things here, is going to assume that there is a certain number of people that are there within some like constant factor. Okay, so you don't know who they are within a factor of 100. Okay, so the chain is going to grow. Sometimes, let me not get into it. There are ways of changing the hardness, and the protocol does it. It's like a little bit more messy. Let me not get into that now. So before the break, let me just mention what the security of this protocol is, and then later on I'm going to discuss a little bit on how to prove in this.
Excuse me.
Yeah.
What is the difference between honest and non-honest guy?
The honest guys are following this protocol in exactly the way it was specified. The non-honest guy is an attacker. He can do whatever he wants.
But whoever prepares a block, which is compliant with the rule, is honest guy.
So whoever prepares a block that's compliant with is honest, and an honest guy also needs to include all the transaction he hears.
Yeah, if I prepare a block.
Yes, then you're honest. If you take the longest chain that you see, you prepare a block that contains, then you're honest. Yes, an attacker is not.
When am I not honest?
Whenever you're doing something that's different. When the attacker controls a certain fraction of players or a certain fraction of computing power, and he does whatever he wants.
But everybody understands that because if I prepare a block,
maybe understand or not, but I'm not concerned about whether you can understand whether you're honest or not. The question is whether being bad enables you to break the protocol.
At least in Bitcoin, people will check that.
Okay, yes, in Bitcoin, right now, I'm just talking about state machine replication. In Bitcoin, you want to enforce certain other consistency property between the transactions, that you're not, that the transactions are well formed. That you can always do that outside. State machine replication is kind of a clean abstraction, just saying I want a list of A, B, and C. Okay, I'm not going to, later on, you can, on top of that, remove things. All right, so what is the theorem? So it actually turns out that for every fraction of players that's smaller than 1/2, so up until honest majority, if you set the mining difficulty correctly as a function of the network delay, then the protocol is secure. So you get consistency, you get some chain quality, and what is chain quality is, I'll get to it later. And the chain grows proportional to 1 over delta like you want. Okay? So what I mean studied appropriately. Okay, actually, let me just mention this chain quality. Chain quality, this number here, what you saw here, this formula, it's not tight. It's not exactly what you want. Okay, and I'll get back to that in the second part of the talk. But roughly it says something like, if the attacker controls 1/3, he can get 1/2 of the blocks. And if he controls less than 1/2, then he can get up to maybe 99, but there's still a small fraction that good guys will get. So even up to 1/2, liveness gets worse the more the attacker has, but it doesn't, it still holds. It slows things down for the good guys, but and we'll discuss ways of like why this is a problem with chain quality and how to overcome it. And just to hint a little bit of why we care about this chain quality is actually going to be for these game theoretic reasons. Since people are spending a lot of computational effort to participate, I need to have some way of incentivizing them, and Nakamoto does that. And really, in that case, having good chain quality is tightly related to whether this protocol is going to be incentive compatible or not. But we'll discuss that later on. But for now, since we're just in a distributed computing world, we don't really need to care about it. We just say as long as you have positive chain quality, you're fine. Okay, so what does it mean that this mining difficulty is appropriately set? The important thing will be that these blocks are mined slower than a network delay. So I need to just set the hardness, I need to set the mining difficulty to be such the whole world combined finds a block much, on average, slower than delta. Okay.
On average or with high probability?
So it's going to be with high probability, actually, right?
Rho is the same as D, so you have to.
Rho is the fraction, the fraction that the attacker controls. So if the attacker controls half of the nodes, then yeah. And so the block time, this is what's called the block time, and in Bitcoin it's set to be 10 minutes. So the mining difficulty is set so that blocks are found every 10 minutes. Okay. This needs to be a lot bigger than delta. So you see, like in practice, people view delta as 10 seconds. I'm not sure where that number actually comes from. It was based on some experiments, I think from the Decker-Wattenhofer paper. And 10 minutes is much bigger than 10 seconds. Okay? And that's good. So how should it be set? I'll show you the formula after the break. But before the break, let me just show a graph kind of like security of the protocol, how it relates to how I set the block time. Okay, so let's C be the block time in terms of network delay. Okay, so block time is C times delta. Okay, so if C, for instance, is 60, that's a scenario we consider with Bitcoin today. So the block time is 10 minutes, network delay is 10 seconds. That's 10 seconds times 60, right? So this graph says that when C, the block time is 60, you're up here, and then it's secure against a 49.57% attacker. Okay? And if you remember whatever Decker and Wattenhofer had this 49 point whatever it was, this number is higher than what they claimed to attack. But when we looked at it, they had some factor 2 mistake in their calculation. And if you actually do it right, this is the attack that they provide. And the attack actually is 49.8. So the analysis seems to be pretty tight there, right, between the attack and the feasibility. And it becomes a little bit less tight when you get closer to network delay. Right, but presumably that's a less interesting regime. And in fact, there is this new very nice paper by Abishalat and a few co-authors that have now a better analysis here too, and I'll maybe mention it later on. So,
they could move to 4 minutes or something like that. I mean, the 25 line is not much worse than.
Yeah, they could, yeah, I guess.
Are they Nothing doing it?
So Ethereum is much more aggressive, for instance. So Ethereum, I forget what their block time is. They're setting it much, much more aggressively. Sorry? Yeah. So I guess maybe they're assuming the network latency is also not 10 seconds. And indeed, so this is a very, very pessimistic model. This assumes that the attacker has full control over the network and can delay messages arbitrarily by delta. That's a very, very hard attack to do, right? And it also assumes that the attacker is, 49.9. Maybe you don't need to be there, right? Maybe it's okay to actually set yourself much lower, and then you can be at a much slower. Okay. So this is the formula, and we'll discuss it after the break.